No sé si habrán subido alguno.
Okay, welcome to the next section. We can start with the posters. It's a very fast talk, about 2 minutes. And our first speaker is Stephanie.
My name is Stephanie, and I work with diagnostic diagrams for classifying agents, and especially I use the liquid diagram, ALMA, the diagram. And in this study is my master's project, and I try to see sample of 2,000 agents investigated by Comfort in 2024. It's a compilation of agents. I try to see if these agents selected in another wavelengths like radio, infrared, stories, and I wrote recognizing the spectrum where they classify in these different diagrams. So I invite all of you to go and see my poster, please. And thank you very much.
Okay, our next poster is Dana.
Hi everyone, my name is Maria, and I'm also Federico. I'm here presenting some results about galaxies, spherical galaxies, and different intermediate values. And we are finding that there is a connection between AGAs and host galaxies in terms of we can observe three different bands across the wavelengths in infrared, radio, and X-ray. And we can see that the AGN is influencing host galaxy, so we can observe some kind of feedback in these galaxies, these intermediate galaxies. So if you have more questions, you can go to the poster. Thank you.
Okay, we can start our session of talks with the first speaker is Violeta Gámez Rosas. She talked on the kinematics of the molecular torus of NBC 1068.
And yes, I will talk about NBC 1068. And I am a postdoc and researcher at the Star Institute in the University of Liège.
I can switch it here. What am I have?
And this really had a very nice introduction by Zihuagn. I will start by introducing NBC 1068. NBC 1068 is a bark square. It's one of the closest agents. It is at a distance of 13.4 parsecs. The mass of the black hole is 1.5 times 10 to the 7 solar masses. It is inside R2, which means that it hosts an obscure agent. It's very light and it's somewhat thick. So, because I'm going to talk about the highest precisions that we can achieve with the parameter, I will start by comparing with what we have heard, again, with the parameters, but in the infrared. So, this is where we see the hottest dust. So, here you should see the dust that is at the two-dimensional areas and the next layers. So, these results by gravity in the K-band to conform micros show this initial instruction where they find this kind of reverse grid-like structure where the radius is 0.25 very nicely the explanation radius, or for reference. And the position angle matches very nicely the position angle of the water lasers, and it has a vertical thickness of 0.14, so it's actually a very thin disk. So this was interpreted as the submission vision because the distances were convenient and because the density revealed a very high temperature of 1,000 Kelvin. But when we work with Matisse observations, again, it's interferently with the LTI, we find in the LM and LMAS, so from previous and microns, we got these initial resolutions. We see the LM and LMAS here in green and the LMAS in red. And one way to explain this image in very general terms is that we are looking at the outer first layers of the torus that we can still see. And why am I saying this? Because if you can see here, we don't have L or M band emission. And this is because it's so obscure that we are not getting the photons from that very dust. So we only see the M band emission, which is the next layer of the water dust. So the position angles, again, I am very the position angles of the water lasers. And in general, our conclusion was that the dust structures align with the classical torus and the modern idea of the dust fields. One important aspect to keep in mind is that our estimate models leave amorphous colors with this frame size and in the black some carbon rays because we have some high carbon features in the element. So, okay. So when it's an observation, we have results that the features. But actually, with the ISM is equals 1% mass in dust and 90% mass. So now when you know what's happening with the mass, with the dust, we can learn the distribution, but with the gas, we can learn about the kinematics, which can be really interesting. So we use the vibration and rotational modes of the gaseous molecules to do this, and we use ALMA. And the very nice thing about this is that both ALMA and Matisse have very similar high angular resolutions, so we can put these side by side and compare. So now what happens when you say, and you see this is one thing, students AGN, because it's very bright, it's close, it's very popular. And so it had been already observed ALMA, and this is work by Garcia with Atlas 2016, where they find the circumnuclear disk with a size of 300 parsecs by 200 parsecs with recent star forming activity, which we can see here. But as we zoom in, this is 70 parsecs, as we zoom in to 7 parsecs, you can see this block. And this was not defined at this track as the dust and molecular gas storage with a major axis of 7 to 10 parsecs. But the kinematics were very interesting because it was showing strong nuclear motions and enhanced turbulence, but also slow radiation and more interesting and apparent counter rotation. So going further, Garcia in 2019 got observations of this molecular gas traces, so CO52 and HCO plus 43 with higher angular resolution of about parsecs. And performing a kinematic model, they found that this framework is really outflow solution. So here you see the outflow, but you also see the torus going around with the rotation. So, okay, these other observations back in the survey in 2019 in the band 6, HCN52, which is another dense molecular gas tracer, also with very high angular resolution of 1.4 parsecs, found this S-shaped radio continuum. This had a flat spectrum and it was consistent with 3 dB emission, but the kinematics again in the inner 1.2 parsecs were consistent with the water megametrics, but outside that radius, again, there seems to be a counter rotation. So now, our observations are also at 7. We have continuum 0 to 2 and 0 plus 4 to 3. Okay, events gas tracers. We analyzed many aspects of it, so like the interdimensional maps, that's of radial velocities, position velocity diagrams, line ratios, and we make kinematic models. Our angular resolution is fantastic, it's 1.6. So this is an image, the first image that we got. Here you can see the contours for the HU blocks for the CO. Yeah, it's very interesting. The colorful stuff feedback is a continuum, and we actually resolved the absorption. The trick to this was actually to do self-calibration and to mass positional baselines. So, going further, here we have the relative velocities of the gas. You can see that we have rotation. So you see here it is redshifted, here is reshifted, but what happens at the other area? We see the contrary pattern, we see blue and we see red here. So again, we find the apparent rotation that in the HCN preview. Now, looking at the light-weights and radial velocities in the molecular gas, we can see that if we trace the different rotation, our movements are very low. And this raises many questions. The first one is why is holding this together? Also, we can see that we have very low line weights. So we were wondering if these were real, if it was turbulent, or it could be an instrument relay. We actually did a roller model playing with the beam effect, and we found that it could be an instrument, but it's just a test, it's not conclusive. So we are going to have this question of if the counter rotation will operate. So when we look at the beam diagrams, we can see that here we have assumption. This is the same assumption that I showed you in the first image. And so we try to interpret this. So we do more kinematic models, and here you can see parabolic trajectories of a filament of clouds that is approaching the black. So this will be the torus, here will be the ambition, this is the line, and that will be in the center. So we found that these three models will actually represent more or less the same as we see here in the position velocity diagrams. This 3D rendering actually depicts the first case that is here. So where we would have like these two elements falling and then just not getting out. So it's very interesting because it could be actually disturbing the torus, which would be nice in a sense, because then we might be able to explain this counter rotation. So we also see the line ratios of the 0 to H2 plus as a common value for the extent is actually a number. And here you can see that we have very, very low values. It's very interesting to see that here these two, where we have the largest value, and actually these pixels go up to 5. Is actually the place where the velocities seem to change, where we have the lower velocities. So, BTF 2014 analyzed the sensitivities of this AGI and they found higher values of 6, 4, and 6 in the eastern north, western north, and around the AGN. So we can see that this is much lower resolution. So it's interesting to see because, for example, when we see a larger sample of AGNs, for example, the new example, we see that the values are again as high as the interstellar median. We don't reach 100, but we reach 40 or 20 or here in the lower values. So why is there like an order of magnitude difference between these two samples? This was interpreted as a very different density radial segmentation inside the dust molecular torus. And I think this is very interesting because we are further seeing to see we increase the resolution with our ALMA. Now, this sample down here, values from 2.8 to 5.7, were expressed or explained as being having the presence of high density molecular graph as already added. So there are 3 different parses from the silicon agents. So I think this is still open. We need more chemical models to really explain what's happening because at the end we need to explain why if there is such stratification, why is there? Why we generate ratio? Why? How do we get the ratio loss? So okay, these are my conclusions. High resolution observations of testing molecular characteristics reveal strong kinematic asymmetries. They are consistent with a combination of rotation, not cloud, possibly involving filaments, and all this is happening here in the resolution state. The line movement and the velocity patterns indicate circular rotation. So this means that we must have something like turbulence, magnetic forces, linear relation pressure, something that is slowing the gas. And but we still need to explain how we keep this together. Because we would expect circular velocities if it was only a rotational effect. So finally, the CO32 position velocity diagrams show a red-shaded absorption. You just see it in the HCO plus particle. It is consistent in both. But it's better around the ring of the signal ratio in the CO. So that's why I mentioned now here. But okay, we see this red-shaded absorption feature, high velocities. So to have the high velocity has to be very close to the background. And because we see in absorption, the only way that we can generate that by having an unfolding function. So this can be interpreted as an unfolding. And finally, I use a movie. It's not a Mexican movie, it's a American movie, but it is about a Mexican astronaut. It's based on of Jose Hernandez, a Mexican astronaut that was an immigrant, and it's a very important story. Thank you.
Hey there, I'm a wonderful talk. So what are the scales of the structure that you're seeing in the dust and also what you're seeing with CO gas? What are the parts scales that you're seeing here? And there are something that's super tiny.
Yeah, it's microseconds, which we have 7 to 10 parsecs. 1 milliseconds is 0.07 parsecs.
Okay, so I mean, as you can see, it's like the best observed, most observed AGN probably because Onyx is positions are close to the way. Are there any efforts to like start combining this with larger scale emissions? So, for example, like Teresa and with Marvel for workout and looking at the year infrared, trying to see if there's inflows in hydrogen and at larger scales. So, are we able to at any point yet start connecting what we're seeing at the small scales to what we're seeing in the emission at larger scales with results spectroscopy?
No, the resolution is just way too different. We haven't, actually, we cannot even make the same observations like in the HGN, there's an outflow, but we don't see it at our resolution in the CO and the HGN loss. So they're yeah, but we still need to find out what's going on there.
It's
It works.
the situation in density is really amazing. I wonder if you and your colleagues have tried to use these complicated kinematics to estimate the gas accretion rate. What you're witnessing is what Andrew Kane called chaotic accretion. This is the reason why by the time you get to the accretion disk, angular momentum is lost. That's why that's uncorrelated with scales. process crazy. If anyone has just have to release stuff. So focus. So you have a perfect setup on different scales. So intrinsically a numerical problem. So you can't calculate for distance. You're witnessing that the dominant mode of black hole was chaotic completion.
Yes, we have multiple cases. Given the infrared observations of matches very results, we don't have yet like a complete model with everything right in transfer and kinematics yet. So it's a very complicated topic. But maybe someone here can learn from some mathematics study or something like that. We will have to talk. More questions? We have time.
I wanted to ask you, are there any other dense gas lines that you have detected with ALMA or only one? Only the
So this work was with CO3 and HCO+43. And the other work that you know of is HDN figure.
Curious about the ACL last night. So you maybe right is an ACL national line. Do you get that as well? An ACL national line. Yes, yes.
Have some lines, some weird lines that are left working really found that they were not really so. And those calculations was not so it's a very beautiful to observe it actually.
last question? No? Okay, if you know, let's thank you again.
Ayúdale con el.
Okay, our next speaker is Federico Espósito. The talk is titled Distribution, the basic error, how alien feedback reshapes in molecular gas complex.
Can you hear me? Yes. Good morning, everyone. I'm Federico Espósito. I just recently started my first postdoc position at the Observatorio Astronomy Nacional in Madrid. First of all, I would like to organize for this wonderful conference in this amazing place. It's my first time in Mexico, and I really fell in love with it. Thanks a lot. And I also want to thank my collaborators, Santiago, Valeria, and Ismael, and all the others collaboration for feedback they gave me on this work. Okay, so the central kiloparsec, and I will talk about local agent mostly, is a dynamic place. It will start with the central engine in subparsec states. And from here, there is the release of several nodes of energy in several ways. And I'm mostly interested in how these different currents affect the molecular gas reservoir of the host galaxy. A phenomenon that we call AGN feedback. Molecular gas is especially important because it's also the main responsible for feeding of the central engine. And within molecular class, we know the star forms. So we also star formation, and star formation comes with some cycle of feeding and feeding. This is a bit complicating everything, but we believe that these pictures are actually crucial to understand galaxy evolution. Molecular gas dominates the covariant mass in the central kiloparsec of late-type galaxies, especially. Almost 100% of it is molecular hydrogen, but this is very tough to observe, especially at low temperatures. So we use the carbon monoxide or CO lines to observe to trace the H2 mass. CO lines, there are a lot of them. The lowest energy one is at 150 gigahertz, the CO1 to 0, the CO2 to 1, CO2 to 2, so on and so on. For the lowest, so here we have the J number, the quantum rotational number that increases 1 by 1 for every line. The lowest J, the low J lines can be observed from ground-based millimeter and sub-millimeter observatories, as ALMA, while for the high J lines, these are targets with reliable cache oscillation. The study of all these lines can give us information about the physical conditions of the gas and the effect that AGN or cell population may have on it. This is the work we published in 2024, and that was the main task of my PhD, was developing this code, which is called Galaxy which analyzes the CO emission of different lines, from CO1 to 0 to CO2 to 12. We estimated, for example, the particular sequence. I will not get into the details of this, but I thought it was interesting to show that for from the mid-J and high-J lines, we find these lines come mainly from the center kiloparsec of these sequence galaxies. The code is public, but I'm currently still working on it, so if you're interested, I'm going to chat. Then I moved to Madrid, mainly to learn Spanish, to be able to come to Mexico one day. Mostly for working many people there, and with the Galaxy collaboration. In the first Galaxy paper by Santiago 2021, they found this interesting correlation between molecular gas concentration, which is measured as the ratio between molecular gas surface density in the central 50 parsec divided by molecular surface density in the central 200 parsec. There is an interesting correlation of this quantity, CO concentration, with the experiment velocity of aging. Last year we published a paper on this target, and you see that 506, which is on this part of the diagram, so you can see that there is a CO deficit in the region. I thought it was interesting also because people will talk later this week about another senior one galaxy, and this is one of them. So in this work, we analyzed oxygen-free emission lines, which is tracing ionized gas, and CO2, which is tracing molecular gas. And as you can see, the oxygen-free, so the ionized gas is extending above and below the molecular galaxy distribution. And we found that this ionized gas had an outflow velocity up to 1,000 kilometers per second. And we believe that this ionized gas wave is related to the CO deficit that we see in the center with the CO line. But most of my talk will be on molecular gas clumpiness. So what is clumpiness? It's quantity to define, but approximately we can think of the ALSM as made of two phases with dense clumps embedded in smooth medium. More realistically, the ALSM shows that structures with smaller clumps embedded in larger and less dense clumps. Why do we care about it? Well, first of all, we know that starting from form in clumps. Then the structure, the clumpiness of the gas can be related to the coupling efficiency, both for the mechanical and the feedback function, but also from cell populations. Also, it is related to the steps and shielding of the gas against external radiation, and it can inform numerical models for fusion. How do we measure clumpiness? So we are using this simple but very powerful technique, Clumpiness in 2003, which they used on optical images of galaxies. You take the original image of your galaxy, which in our case it will be the CO2 map observed by ALMA. Then you smooth it to get a blurred version of the same image, and then you subtract the second from the first, and you see the clumps merging. Then the constants can create a numerically this clumping parameter defines unrestricted. So we use the same technique applied to the images. This is an example for ABC57, which is one of the galaxies analyzed in the Galapagos sample. We just added an intermediate step since we did this exercise for 16 different galaxies or local agents, and we first uniform the spatial resolution of all of them to the worst one, which in our case was 16 passes. Then we smooth them. This is an example with a 50 pascal P, and then again we subtract and we get this clumping sound. The two ellipses that you see on every image are the circles we regulate 50 and 100 passes projected onto the galaxy plane, and those are the same ellipses within which the same apertures within which the zero gas concentration is being measured in Santiago. So we could compare with those results. But one question is, of course, how do we decide to smooth 50%? We don't. We tried this with a varying smoothing size between 20 and 100%. So I will just show you these plots. This is 20%, 30%. As you can see, most things changed in the last month, the first they didn't change. And you can see the clumps most growing size, they connected with some are, for example, this one is shrinking in size iterates. So we think that by doing this, by using different smoothing sizes, we are tracing clumps of different sizes, mostly going from general network clumps, GNC, to GNC associations. So this method analysis actually middle one. It is very powerful, but it has, in my opinion, a problem, which is that in some cases it's giving high values for high contrast region rather than clumpiness. So to overcome this problem, we developed other two methods, which use the same initial technique, but they change the last one. So another one is to calculate the ALMA speed within a certain amplitude, for example, the linear 50%, and then by the value of the flux within the same amplitude, we get integrated values. And another one, method 3, is to calculate directly the flux within these clumps, so within these contours, without subtracting and divide it by the total flux within the signal. Of course, this curve method gives higher values because we are not subtracting for them. Okay, I will just see this because we lose time. So we did this for this sample of 16 galaxies, all observed by scheduled line. We first plotted them to 16 passes, there was common resolution. And so So these are the results. This is for smoothing of 20 parsec with the 3 different methods. And we try to compare. This in this case is the nuclear one, measured in the center 50 parsec with the X-ray luminosity of the targets. As you can see, by smoothing at 20 parsec, we do not see any trend. But starting from 30 parsec, with the third method, we see a breakpoint in the relation between Clumpiness and luminosity. Here we are using this one's linear 50 for 50. And at 60 parsec, we see the same breakpoint around 10 to the 42 microsecond appearing before method 2. And at 90 parsec, we see the same for method 3. So since these are all of them here. Since 90% was the one where we found the breakpoint for all the 3 methods, we estimated the 95% confidence interval with observations taking into certain piece of the data, and also we validate the position of the breakpoint with only 1 out cross validation, which literally exclude 100% from the fit. As you can see, with method 1, the breakpoint is not very stable around the position, it is moving by more than 1x, but for the other 2 methods, it seems very stable, so we trust them more. So to summarize, we are seeing another trend of breakpoints versus its luminosity, similar to the one with concentration measured by Sandy in 2021, which we talked about standard sample. In this case, we find it only with the Clumpiness measured within the center of 50%, so very nuclear region. And the breakpoint is again around 10 to the 42%. So we believe that this history luminosity is particularly important for method as feedback in these targets. This paper we just published last week on the archive, and it has been accepted for publication in some statistics. Just to mention, in the meantime, we launched an ALMA proposal to extend the parameter space of the X-ray luminosity and the ratio to higher values, and we plan to observe these 6 traces from the region process sample already analyzed by 2021, but going from a kilopascal resolution to 50 to 1 pascal resolution scale to measure this concentration and acceptance on these targets. Just take my conclusion because I'm really late. I just want to welcome the presentation. So, it's not my favorite Italian of all time, but probably the one that I think no one has heard about. It's a bit old, but it's not long. We can consume blue planet in English. It's not a documentary. It has almost no human voices. There's almost no music. And unfortunately, it has no words. Thank you.
Thanks for a great talk. So I was curious about the relationship between coupling and how that might affect these facilities, and also the communication that we're observing from these galaxies. So some of the ones that you didn't think that were like the least clumpy, like 4388 and 506 are edge-on systems. So you're kind of seeing like the whole disk in like a line. So could the orientation of the most disks here be affecting how clumpy or unclumpy they are versus the X-ray luminosity?
Yes, actually, to avoid all this, we excluded 3 targets with very edge-on. So GC556, GC4388, and I think GC8008. So in this, basically, those are the only 3 targets that are not here assigned here. These are the targets from our machine above 75 degrees.
I think they're like in the last year so far. So what was the last year that had them? That was like one of the final plots that had them? right? Down, so, oh, that's looking at it on papers, got it, okay.
Yeah, exactly. Those two are. In fact, in kinematics, extremity ones are distributed to some assisted some values, which is some values was mentioned kilos values. We decided to exclude those very heavy parts for this week.
Yeah, I'm wondering about this strategy at companies. I understand that you developed originally for using data, but now you're using it on strategy. So do you test is that as a valid thing to do?
We are testing it, but it's not the first time that it has been used on mathematical data. Actually, there's a paper by Yamamoto Tal 2024 in which they analyzed trans data with the same technique, and they found some interesting results.
I'm very interested in what is the physical origin of clumps. For example, is it due to repetition? For that, one of you correlated the these physical properties of the clumps with local gas fraction and also the shape of the rotation of the two rates to the clumps.
Not yet, but this is of course an interesting thing to do. First thing that we did was to perform a calculation and to see that there is a trend. The physical explanation on this is really
so the mass function would be really interesting. This is a unique relationship with the mass function, and whether the constants that obey the Larson relation, size, mass, and velocity smoothing would be higher diagnosis, the origin.
yeah, thanks for your suggestion.
I have another question. We should talk later because we have very similar research interests. But so for this slide here, is there any consideration in terms of for molecular clumps that may be due to streams or inflows of gas that might result in clumpiness of molecular gas, but is also indicative of strong Asian feedback? So you have stream inflows. Does that play a role in how clumps may be perceived? If that makes sense.
Yeah, it makes sense. So for some of these galaxies, we have they studies about the molecular kinematics. For example, we see that type 6 and many of them. And actually, we are in the process of analyzing also Zihuagn emission lines, so we will see the kinematics of the gas. I can tell you that in some of the targets, there are clear indications of output moments. So the gas is, in most of the cases, the gas is protecting it, it's flow.
Please.
Clarify the region with gases. I said, but the gases that show the most streaming will scale because this is all part of molecular. This is create information. Because of this disturbing feature, for example, gas representation, molecular gases here after usually speak.
Okay. Thank you to Federico.
Sí.